Hello, everyone, and welcome to today's webinar, Advanced Catheter Design Techniques. And before we get started, I'd like to go over a few items so that you know how to participate in this event. Audio for this webinar is streamed through computer speakers or a mobile device. You can select the speaker output and the audio section of the GoToWebinar control panel and then adjust your volume through your computer or mobile device volume settings. Throughout the presentation, you can submit any questions that you have to our speaker by typing them into the questions panel. And to access that panel, click the questions icon at the top right and just open that up, and then you can type your questions there. We will address your questions during the Q&A portion at the end. And with that, I would now like to introduce today's presenter, Jordan Mason, Staff Process Engineer.
Thank you for that introduction. So let's get started here. Thanks for everyone for joining. We're going to go through some discussion about advanced catheter techniques for designing and developing catheters. We'll go through this agenda. We've got what is a catheter, just kind of the basics. The anatomy of the catheter, and what makes up a catheter. Some design approach elements, choosing the right liners. Choosing the right reinforcement layers, whether you're going to do braid, coil, or a combination of the two. Outer jacket selection for the different types of polymers that you can use, and then some of the fillers and additives that you can put in those to improve the performance of those materials. So just kind of the basics of what a catheter is. We've got the Merriam-Webster dictionary version of what a catheter is, but obviously a catheter is far more complex than what that can cover. There's a lot of different types of devices. I think when you talk about catheters to people, a lot of times people that don't know about catheters instantly go urinary catheters or Foley catheters because they don't know better. And obviously those are kind of as simple as it gets in our industry. And you see to the right here, we have a picture of kind of one of the more complicated devices on the market in the Abbott clip. It's a steerable device. It has multiple steering points and multiple planes of deflection. And it's doing a lot of things. Now, in this presentation, I'm not going to go into detail on steerable catheters. I could do 45 minutes on steerable catheters all by themselves. So we'll start here, and maybe that'll be a discussion for a later date. And so here's kind of the anatomy of the three basic types of passive catheters, non-steerable catheters. We've got a braided catheter, a coiled catheter, and a braided and coiled catheter. And so these are going to consist of some sort of a liner material. We'll go into more detail about those different types of liners further down in this presentation. And then we've got a braid reinforcement layer. Now in this picture, there's only one braid reinforcement layer, but you can have more than one. You can have multiple layers of braid if you need that kind of reinforcement. And then we have a jacket layer. And these layers are not just sitting on top of each other. The jacket layer, when it goes through a reflow process, will be inside the space between the braid elements. Then we move on to the coil construction, basic construction, liner, coil on top of that, and then a jacket over that, which is again going to fill the space between the coil and create a complete composite structure. And then we have the combination of the two, which again, we have braid, we have a liner, we have a coil, and a braid. You can flip those back and forth depending on the performance, and we'll talk about that a little bit more later. It doesn't have to be coil then braid or braid then coil. You can manipulate those, and then a jacket. So this is kind of the basic design approach, right? We're going to collect and establish the requirements. We need to identify where do we want our device to go. What needs to go inside our device? Does our device need to go inside another device? And what kind of a tortuous path is it going through? And that's going to help us to kind of define what our starting point is and where we want to get to with the design elements that we're looking at. So we'll want to specify the liner. That's the material, the geometry of the liner, and the manufacturing method of that liner. We'll go into a little bit more detail on that in a minute. We're going to specify the reinforcement layer. Again, what material type are we talking about? Are we talking about braid? Are we talking about coil? Combination of the two? What are the geometries of those materials? Are we using ribbon? Are we using round wire? What are those sizes? And then the assembly method for those. And then we're going to talk about specifying jackets. So again, it's the material, what polymer are we using, what kind of process is that being applied with, and what additives are we going to put in that. Then we're going to specify the heat shrink materials. There are a few different types that have their pluses and minuses for different applications. And then we'll do a shaft design analysis. We'll do some calculations. We'll do some testing. There's ways of getting theoretical data. There's some systems out there for doing that that'll simulate what the outputs of your construction are. But realistically, those all have, like anything in physics and math, there's variables that are hard to account for, and so they're not always a perfect system. So realistically, testing parts at the end, going through 3-point bend tests and axial rigidity tests and those kinds of things are going to be your best way to really evaluate the performance of the device. So we'll start with aligners. There's a lot. This is very verbose. I'm going to go over this. This is really for informational purposes for you in the future, but I'll talk through the more important points of this. So the most commonly used material on the market for catheters, for good reason, is PTFE. There's two different ways to get PTFE. There's the ram extrusion process, which some of you may not be familiar with what that is. Ram extrusion, PTFE is not melt processable, and so you can't keep loading it into a screw and pushing it through a hot die and continuously get tubing out of it. PTFE doesn't melt, and so it has to be created, it has to be sintered, and so you get a bunch of PTFE particulate in various sizes and structures, and that gets put in with other agents that bind it together. That gets put into a ram extrusion process, which essentially is like a hydraulic ram. Think about a Play-Doh press where there's a finite amount of material in there and it gets pressed through. And so that has some limitations because it's not a continuous process. Your lengths can be somewhat limited. The amount of continuous length that you can get is very limited, depending on what size it is, especially if it gets big, it gets much shorter runs. So the PTFE is the other way is film casting. And so that's where the material is suspended in solution, and there's a specific process for that where they're running a mandrel through that suspended material and sintering that through an oven. So that is actually a continuous process. The problem with it is it's a little bit weaker because there's no orientation of the fibers like there is in an extrusion process. And then it's limited in size because it has to go over a core. That's a continuous process. That core has to pass over rollers and pass through the process. And really you're limited to about 90 to 100 thou. There's some companies that are kind of pushing the limits of that with different types of core materials. But in general, you're talking about less than 90 thou in diameter for the ID of the liner. Film casting also can give you much thinner walls because those layers that are being applied are in the tenths versus the thousandths, and the precision is much higher. The tolerances are better. So there's good applications for both RAM and film casting solutions. They're not necessarily interchangeable in all applications. PTFE is the most lubricious material that we can use, and which is why it's used so much. There really is nothing remotely close to fluoropolymers when you're talking about lubricity. The ram extrusion liners are a little bit stiffer, and the film casts are less stiff. So film cast liners are a little bit weaker, a little bit easier to pinhole, a little bit easier to burst. So again, kind of your applications depend on what you're looking for. PTFE has to be surface treated. It does not stick to anything when it's untreated. PTFE is an inert material, so all of the bonds molecularly are completely accounted for. All the electrons have their mate, and so there's no surface energy to grab onto other types of materials to adhere to them. And so what happens with PTFE is it gets etched, typically with a chemical called sodium naphthalene, and it's just ripping off some of the material from the molecular bonds on the surface and creating some energy. making some electrons that are not accounted for. And so when you go to refill your materials over the top of it, they will bond to that. Etchant doesn't last forever. It can be, as soon as you start to create that surface energy, oxygen and other things try to bond to it. And so it wants to get back to an inert state. And so PTFE does have a shelf life. And how you package that extends or reduces that shelf life. The big problem with PTFE, and it's becoming a much bigger problem more recently with EPA cracking down on ethylene oxide, ETO or EO sterilization methods, is PTFE cannot be run through radiation type sterilization methods. The radiation breaks the bonds in the molecule and it turns to dust, and it is no longer the liner that you put in the product. And so it's limiting to use PTFE because you must stick with ethylene oxide or some of those other similar types of sterilization methods that are not radiation based, like gamma or E-beam. And that's the same for RAM or film cast. It doesn't matter. It's the molecule of PTFE that's breaking down in that process. And so we get a lot of requests for non-PTFE based materials. There are some fluoropolymers in this list below PTFE here that are stable through gamma and E-beam sterilization. I think one of the most common requested is FEP. FEP is a melt extrusion so you can run continuous runs of that. The problem with FEP and PVDF and PFA, they all have the same issue, and that is it's difficult to get very thin walls, right? So standard with PTFE is to get 1 thou wall thickness or even less, especially if we're talking about RAM extrusion, getting it down to 5/10 of thou in wall. You can't extrude those other materials to that level of thickness. They're going to be in the 2, 3, 4 thou range. It's difficult to get down to 1 thou range in those extruded materials, and so that's where they become less preferable, because usually we want the liner to be as thin as possible because it is a fairly stiff element. But there's applications where you don't care. The stiffness is fine, the thickness is fine, and you can get away with using one of these other materials and be able to get away from using ethylene oxide and use gamma or E-beam sterilization. Now, the other problem with them is PTFE reacts very well to surface treatment with the etching. The other materials don't react as well. You can get a bond, but the bond is not as good. And so we've seen a lot of issues in industry with you trying to use FEP and PVDF and PFA, and the etchant doesn't give you the best surface treatment, and you end up having some delamination issues, especially in devices that need to be pretty flexible. The more strain that you're putting on that, the more likely it is for that to fail. So that's why we don't see them used very often. They get used in kind of special cases. People are trying to use them more frequently, but it's difficult. And so again, PTFE is the gold standard for the most part. So other things that we've used in the market are non-fluoropolymer. Biggest problem with these is you're not going to have the lubricity that you're going to get from PTFE. But for a lot of applications, you can get close enough, and especially with additives. You can get close enough and they'll be fine for the application that you're doing. So polyimide is a good one. It's not that far off from PTFE. It's certainly less lubricious, but it's a pretty good material. It's not as tacky as like a thermoplastic would ever be. And you can actually dope it with some PTFE that doesn't have a problem with going through gamma because it's just split anyway, so it's already broken down. This is polyimide is a thermoset. It is broken into solution. It is not a thermoplat. You cannot melt it. So it's typically film cast. It's broken into solution, laid onto a mandrel, just like the film casting that we're talking with for PTFE. It has decent lubricity. It's got great dielectric strength. It's a very stiff material, which is why it's not used as much, because it's significantly stiffer than PTFE. You can get it in very thin walls, because it's that film casting process, long continuous lengths. Again, though, you're talking about issues with it being small. You're limited to that roughly 090 type diameter. So you're not going to use it in bigger devices. It's pretty cheap. You can get it thin. It's great for really high pressure applications, again, because it's stiff. and so it actually has very high burst strength. And you can gamma and e-beam sterilize it, or ethylene oxide sterilize it. So it's very versatile in that respect. The adhesion on is not fantastic, again, because it's not melt processable. You don't etch it. So you're mostly relying on kind of a mechanical bond to your jacket materials, but it's decent. And a lot of times what you'll see in continuous processing polyimide is they'll do a polyimide layer, and then they'll do a reinforcement layer, and then put polyimide back on top of that. And so you've constrained your reinforcement layer and don't have to worry about that delaminating. So then we have the polyethylene family. So we have high density polyethylene, low density polyethylene, and polypropylene. They're lubricious, they're cheap. The problem with them is they don't play nice with anything else. So you really have to stick within the family of those materials to get to process them. They're really commonly used for dilators, introducer sheaths, and types of devices like that, where you're just using a single material. You don't need to have a stack of a bunch of materials. And they work fine for that. They're melt processable, they're gamma e-beam sterilizable, they're screw extruded, so they can be done in high volume and long continuous runs. Again, the material's very cheap. It's not as lubricious as fluoropolymers, but it's very lubricious. It's also quite inert, very chemical resistant. And if you do want to use them with other types of materials, you can't use them directly. You have to use a tie layer technology. And so there's some materials that can stick to HDP, LDP, and polypropylene, and then can also stick to other materials. And so that's where you start talking about multi-layer extrusions, which are expensive. So you start adding a lot of cost there. That's why you don't see them used that much unless they're being used as just the one material. And then lastly, we've been using a lot more of this more recently because of all of the new additives that have been coming out that have really been making the use of thermoplastics more feasible. Because in general, thermoplastics don't have good lubricity. They're screw extruded. You have a whole lot of different materials that you can do. You can also film cast them. The materials are generally low cost, some more expensive than others. With additives, you can have decent lubricity. Again, it's not going to be as good as any of the other materials on this list. It's not going to be as good as HDP or polyimide or PTFE or FEP. But again, in some applications, it can be reasonably good and good enough for that specific application. And we've been using them more and more, especially again with the additives that we can put in there that make them pretty good. You can run them continuous discrete. You can gamma EO and run through all sorts of different types of sterilization, and they're pretty easy to assemble, reflow, melt, just like we do with the rest of our jackets as well. So we'll start going into our reinforcement layers. So this is a braid reinforced shaft, and some of the considerations there. Why would I choose braid? Why would I choose coil? Or why would I choose both? And there's a good reason for it. Braid reinforcement is going to give you a structure with better longitudinal rigidity, better flexural rigidity, and better torque response. You're going to have more burst strength. You're going to have less ovalization than having no braid at all. And you'll have improved kink resistance, again, over having no braid at all. For material selections, there's a lot of different materials they can use. There's really common materials, and there's some more commodity ones that we play around with in certain applications. Most of the time, you're going to be using a metallic braid structure. Most of the time, you're going to be using stainless steel. But there's times where you might want to use nitinol for its shape memory and better kink resistance. Tungsten material for its visibility and strength. And then there's more rarely you'll see some other materials like tantalum and stuff like that that are very infrequently used because they're expensive and not needed most of the time. And then you're going to have polymer fibers. So there's devices that need to go through MRI compatibility. You can't run these metals through MRI. You'll make a mess. And so there's polymer fibers that you can use in those applications in replacement of your metals. Now, in general, they're not going to have the same performance that you're going to get from a metal, but can be good enough for the application that they're going into. So there's aramid fibers, there's PA, polypropylene, PET, LCP, PEEK, and there's others out there, but those are kind of the most common ones. You have to think through these. Some of these are melt processable, which means they're not going to be good for a device where you're overlaying a jacket that has to be reflowed because you're going to melt your braid. Things like LCP and PEEK and Kevlar don't melt, or at least don't melt within the temperature ranges of what your device is going to get processed on for jacketing it. And so those are good for those applications. And some of the other ones you would be looking at like dip casting or some other type of process around them, where you're not worried about melting the braid structure. Some of the design considerations, obviously braid has a few different elements that make up its design. A lot of these are dictating braid angle, but we don't ever talk about braid angle. Really what we talk about is the pick count. So picks per inch or picks per millimeter. Picks per millimeter is not commonly used anywhere, even in Europe. Generally speaking, most people call it picks per inch, kind of a standard. The textile industry is its own animal and has its own, its own nomenclature. So PPI is what we use. And so that's the number of times in a linear line across the length of the braid, not radial, but axially, the number of times those wires cross each other, or each one of those is a pick. And so you add up the number of picks in a unit of length, and that is your picks per inch or picks per whatever unit of measure you're using. And so the PPI dictates the flexibility, the torqueability, the longitudinal rigidity of the device, obviously in conjunction with whatever wire type you're using. But in general, we want to stay below a 70% surface area coverage. And the higher the PPI, the more crossings per inch you have, the higher the braid angle. And that means you're going to have higher density of braid within a unit of length. And that means the wires are getting closer and closer together. And so you're going to run into a surface area problem. And with braid, you need to be able to get the jacket through the structure. And so if you have higher than 70% surface area coverage, you can see it's difficult to get the polymer to flow through those tiny little spaces between the wires. And so it's kind of our upper limit of what we want to do. Now with PPI, there's a point of diminishing returns with PPI. It's not just the higher you go in PPI, the more flexible it gets forever. It's a bell curve, so there's a point of diminishing returns. There's some simulation software that can be used, CAD namely, where you can do a pick count macro and it'll show you where that inflection point is, where it starts to get stiffer again. And so that's kind of your upper limit. We would say, all right, don't go any higher than this. And then we have different braid patterns. And so the most commonly used machines out there are Steger braiders. You can get more information from some of their webinars as well. They're kind of the experts in this space. But we have 3 basic patterns that can be done with Steger braiders and pretty much all braiders in general. We have a regular pattern, which is 1 wire that passes under 2 wires and then back over 1 wire again. So back over 2 wires again. 1 under 2 over 2 for short. And so that's got a little bit of freedom of motion because it's not every single wire passing up and under and over another wire. You've got those pairs, so it does flex a little bit more. It does have a little more freedom of motion. Problem with that is it's not as good if you're doing transfer braiding. Because of that freedom of motion, your braid can kind of go awry a bit if you're doing transfer braiding, which transfer braiding, if you don't know what that is braiding onto a mandrel or a core and making that a little bit bigger than your device and sliding it off of that core and onto your device so that you're not having to run braid stick-wise in your process. So it'd be a little bit more efficient way to do it and more cost-effective. Standard braid pattern also runs the fastest because it has every single one of the carriers has a wire set up on it. Versus half load, so that's the next one we'll talk about. Half load is 1 under 1 over 1. So that's what I was talking about with on standard, we have the 1/2, where we have a little bit of freedom of motion because it's not every single wire intertwined. Half load is every single wire intertwined. But to do half load, you take half the wires off of the braider, and so it runs slower. If you want to run a 16 wire braid in regular, you load up all 16 carriers on a 16 carrier braider. If you want to run 16 wires in half load, you have to use a 32 carrier braider and run half the wires. And when you have a 32 carrier braider, the circle that those carriers have to pass through is twice as big. And so the distance to go around is much longer, and it's a lot slower process. And so half load tends to be more expensive. It's definitely more expensive because it's a slower process. But there's some performance benefits to it. You're going to get more flexibility out of the standard pattern, reasonably similar flexibility out of the half load pattern. You're getting some trade-offs here between kink resistance and compression strength. The most commonly used is going to be standard, probably why it's called standard. From the testing that we've done, and with both the theoretical and the physical testing that we've seen, 95% plus, you're going to use regular pattern. It's really kind of some of those outlier cases where you really need just that last percent of difference that you're going to get out of changing the pattern. But really, it's kind of a waste of money most of the time. It's just stick with standard pattern. The last one is diamond full load pattern, and so that's where 2 of the wires get paired up. And so you have 2 under 2 over 2. That one's used when the problem with that pattern is it's pretty stiff. It's not as efficient because you're running, to get the same PPI, you're running half the density. You're going to have, it's really good for burst and for kink, and it's got a lot of torque, but it's not very flexible. And so you're not going to use it in the ultra flexible devices. So we use it, we don't use it commonly. It's really expensive, but it's still a pattern that you can use when you need that performance out of it. We have triaxial sitting here. That's not really a braid type, but it's something that you can do on a braider, and that's just running a axial fiber or multiple axial fibers within the braid, and it'll intertwine it axially as it goes along. Those are used to give you axial rigidity, but they hurt you in flexibility because you get, if you only use one fiber, you get bending bias against where that fiber is. So it's we don't use it very often, but it's very specific applications where you're looking just for really high axial rigidity out of the device. So as far as the next part is what type of wire are we going to use as far as ribbon or round? Ribbon is used more commonly than round in all devices except for maybe some of the micro catheters. And that's just because round, to get similar performance out of it, takes up a lot more space than ribbon as far as wall thickness is concerned. And obviously in this industry, we're always looking for the thinnest device possible. And so we don't usually have the wall thickness to allow us to use a round wire. One of the problems with braid is you've got wires that are crossing over each other. And so the diameter of or thickness of the wire is 2x when we're talking about the wall thickness space that takes up. We can also run single filer or multi-filer in braid. Obviously, single filer is the most common, but there's times when you want to run a multi-start on a single spool, and essentially what you can get is you can take 3 round wires that would be equivalent to a ribbon wire of the same dimensions, roughly, right, thickness and width. And you'll have a lot more flexibility there because you have 3 independent wires stacked side by side. And so those can flex about each other. Not as commonly used, generally used for really high flexibility while still maintaining pretty good torque and axial rigidity. It's more complicated, it's more expensive, it's more time consuming, but it has its uses. We can do double start, triple start, quad start. There's a few different options there. For round wire, we're typically talking about less than 5 thou. There are cases where you're going to run bigger wire than that. For most devices, we're talking about 5 thou or less. For flat wire, again, because when we're using a 5 thou wire, if you add that 2x, you're talking about 10 thou wall being taken up by that round wire braid. And so you have to account for that, plus get jacket over the top of it, so your wall thickness gets quite thick. For ribbon wires, the smallest one that is typically used is half thou, again, 0.0005 by 2.5 thou. You can also get half by 3. Then you have 1 by 3, 1 by 5, 2 by 6, 2 by 5, 2 by 6. And generally speaking, one of the biggest ones you're going to use is 3 by 7. There are bigger wires. I have used bigger wires, very uncommon for very specific applications. But this is kind of the range that you're talking about that's most common. And these wires are typically available off the shelf from companies like Holbrick and a few other places. So it's pretty easy to spec them in and develop them and not have to wait 8, 12 plus weeks to get a custom wire that you call out. And that brings me to a point. When you're specing out a catheter, try to stick with standard sizes of things, especially wires, because their lead times are long if you ask for custom. And it just makes it more expensive. It makes it more time consuming to get your product. Is that? Oops, I need to fix that. My slides. That's redundant. All right, we'll move into coil reinforcement. So big difference between coil and braid. Coil is used more heavily for hoop strength when you want to make sure that the inner lumen stays round through all tortuosity or through the handling of the doctor. The coil will give you much better radial strength, and so it's harder to pinch it, it's harder to crush it, it's harder to kink it. And it's also very flexible. So braid is flexible and you can get it pretty flexible, but it's never going to be as flexible as a coil because you don't have those wires crisscrossing each other and constraining each other. They're really just there for support in the radial direction. Same concept apply when we're talking about metallic versus polymer. Usually you're going to use metallic. Most of the time you're going to use stainless, although nitinol gets used pretty heavily in coil, especially in microcatheter applications, because it is even better in kink and hoop strength than stainless steel is. Sometimes you use tungsten, sometimes you use other precious metals. You can put coils of precious metals instead of using marker bands. It is a marker band, sorry, instead of using a band, a solid band. Again, that can give you some more flexibility. You can carry one size of platinum wire and use it all over the place for various length bands because you can just wrap more coils of it. And obviously getting marker bands is challenging, has been challenging for a long time. There's only a few suppliers and lead times are very long if you want it custom. Polymer fibers, you're really not used very commonly in coil, but if you need it to be MRI compatible, you need to go to some sort of a polymeric fiber. Same ones that you would have used for the braid. They're not going to give you the kind of performance in hoop that you're going to get from a metallic element. So we're talking about coil angle. Again, really not called out in coil angle. What we're talking about is pitch. So the distance from the center line of one coil to the center line of the next adjacent coil, not the gap between them. You can call it gap if you want, but that's not what pitch is. And then the other way is wraps per inch or wraps per millimeter or centimeter, whatever people are using. More commonly wraps per inch, again, even in Europe, where the metric system is more commonly used. Still usually called out in wraps per inch. And that's just pitch over, it's 1 over pitch. The nice thing about using that is you get, when you're going to inspect it, if you're asking for pitch, you're going to want to have them go measure a bunch of spots of pitch, and you have to do that under higher microscope. You got to use like an OGP because we're talking about thousands of an inch of measurement here. If you call wraps per inch, you get an average, right? So it's a lot easier to measure it. You can go in there and you can even go in there and just measure, in a 1/4 of an inch if you're talking about really high wraps per inch and multiply it out. It's just an easier way to actually measure it in process versus using actual pitch. In general, as the pitch goes down, so as the wires get closer and closer together, the flexibility gets worse because the wires start to run into each other when they flex. But the kink resistance goes up because you have higher density of metal, harder to pinch all that metal down. And then vice versa, when you start talking about increasing the pitch, moving the wires further and further apart, you're going to get better flexibility, but your kink resistance goes down. You do need to consider surface area coverage for coil, just like for braid. Again, don't like to go above 70%. And honestly, with coil, you probably want to stay even a little bit lower than that. And then typically you're going to see the coil pitch along the length change to change the performance within specific segments that are going to be passing through specific parts of the anatomy. For microcatheters, you're going to see the disc. It's going to go from a pretty much stacked pitch or very close to it in the proximal section, and as where you want it really stiff and you want to have really high kink resistance, mostly for physician handling, so they don't crush the tube. And as you move towards the distal end, where it's got to go through really tortuous anatomy, you're going to see that pitch increase to allow it to flex more. With coil patterns, you can actually do multiple layer coils as well. It's not as common, but it does get used periodically. It gives you a little bit more torque response when you have the coils wrapping back and forth in opposite angles, right? So they cross. It's not like a braid because they don't weave in and out from each other, but you do get some of that torque response back that you lose, because in general, coil has no torque response, especially in one direction. The direction where you're unraveling the coil has no torque response, essentially, other than what the polymer gives you. But when you torque it towards the direction and it actually starts to tighten the coil, you do get a little bit of torque response out of that. Still nothing like what you're going to get from braid. But if you wrap them back and forth, you start to have the coils constrain each other. And so one's trying to loosen up, but the other one's trying to constrain down on it. And so you get some of that torque response back. One thing to consider when you're using coil, it's difficult to coil directly onto a thermoplastic. You can coil onto the thermoplastic, but if you're going to use a melt process to put the jacket over the top of it, you're also going to be melting the base layer, right? The liner underneath it. And when that happens, these coils are under tension. There's a lot of forces in them. And as soon as they get loose, the coil will just start to shift and sway all over the place. And so you lose your pitch consistency. So it's difficult to use thermoplastic liners with them if all you're using is coil, and all you're doing is putting coil directly onto that liner. Usually you want to use a solid, stable layer, a PTFE, a polyimide, an FEP, any of the materials that don't really melt within the process that you're doing to put the jacket on. And similar to with braid, you're going to use rounds or ribbons. Both are used commonly. It just depends on the application. Rounds are used more commonly in smaller devices. Flats are used more commonly in larger devices. You can do single filer or multi-filer. Most commonly single filer, but sometimes multi-filer is used. Problem with using multi-filer is there's only very specific machines that can make that. And so most people don't have that. There are some design benefits to using multi-filer, but in general, single filer is fine. You're talking about half thou up to 5 thou most commonly. Again, they can get bigger, but not as common. Flat wire, same as braid, but they do tend to go bigger than braid. You're going to start somewhere around 1/2 by 2.5, and really commonly used 2 by 12, 4 by 12, sometimes even a little bit bigger. But 2 by 12 and 4 by 12 are really common, especially in some of the mid-sized devices and larger devices. And then some of the smaller coils, 2 by 6 and whatnot, are used for some of the smaller devices. There's a couple different machines like I was talking about there that when you're doing multi-filer, it's less common. There's a standard coil winder. We manufacture one. MMT has one. There's Rothgreaves makes one. There's a few different machines out there on the market at varying expense. Standard coilers are discrete, so you're taking a stick, a mandrel, a core, a hypo tube, whatever your mandrel is, and you're clamping both ends of it within chucks, and you're loading a wire type on it and wrapping the coil on your discrete segments. Then there's an attachment for the braiding machines. They're slow. They're used generally for continuous processing only because, again, they're a lot slower than using a discrete coiler. But you can have reel-to-reel operations with that, and so there's certain applications where that's good and useful. Then there's again, there's multi-filer options, and there's the easiest thing to do a multi-filer on is the braider and coiler, the braider hybrid system, because you can load up coils. You can load up, I think, 8 or 16 or however many wires on that and do a high number of starts with that. With a standard coiler, though, the heads are very complicated and they have tension control mechanisms for each wire. And so when you start adding multi-filer, each one of those needs its own tension mechanism, and it gets very expensive very fast, and the machines get very complicated. Now, there are very big multi-filer standard coilers out there. Rothgreaves makes some, Engineering by Design makes a few, but again, very expensive and not the typical. So then we have braid and coil. And so this is where we can kind of get some of the benefits of both. You lose some of the stuff that the coil gives you as far as extreme flexibility, but you get a bunch of the performance benefits that the braid provides. And these are commonly used in some of the smaller microcatheter devices, definitely used in steerables. I won't go into detail about that, but really commonly used in steerables. The coil, again, adds a lot of crush resistance. So if you have a lot of physician feedback that they're crushing your tube, adding a coil in there, they can make a really big difference. If you have a lot of flexibility, you need to have axial rigidity and you need torqueability, but you have a flexible section that goes through a pretty demanding section and it likes to kink and collapse, a coil will make a big difference in that application. So again, the material selections, there's nothing different, right? You're just trying to figure out how do I get all this stuff within the wall thickness that I need to achieve. And so that's where it's going to kind of push you in one direction or the other with the thicknesses of these wires, or ribbon versus round, etc. So now we move on to the jacket materials. So, right, this is what finishes the structure and makes it all one. There's a lot of different materials. There's a whole bunch of different reasons to use specific materials over others. There's thermoplastics and there's non-thermoplastics. Generally speaking, when we're talking about these jackets, it's thermoplastics, but there's some applications where we might use a heat shrink, a PET or an FEP or something like that, or even a PTFE heat shrink or a polyolefin heat shrink as an outer jacket layer. Those are specific applications. It's not the most common. Most commonly, we're talking about using thermoplastics where we're filling in the structure around our braid and coil. And we're doing a melt reflow process or a deposition dip cast type process. Most commonly used is P-backs. It's cheap, it's readily available. It works for most things really well. The process, it's very processable. It's easy to melt. It doesn't have a lot of quirks and challenges with processing it. And it's just, there's a lot of data out there on biocompatibility and all those types of things. So PIBA is used very often. P-backs is actually a name brand by Arkema. So PIBA is the general term, polyether block amide. A lot of people don't realize that. There's a few other manufacturers that make PIBA besides Arkema, but Arkema is certainly the most common. There's a lot of there's polyurethanes, PUs, also known TPUs. So these are thermoplastic polyurethanes. There's benefits to using thermoplastic polyurethanes, especially in the lower durometers. The problem with P-backs, it stops at 25D, which is about 80A. But the 25D material is very sticky and does not perform very well. So that's where you're going to start thinking about switching to a polyurethane if you want to go softer than that, or get a little bit better performance out of that 25D, 80A range material. Polyurethanes go all the way down. Natural polyurethanes are going to go down to somewhere around 70A, and then some composite type polyurethane polyblends will go all the way down to 30A or 25A. So they get really soft, closer to the silicone range. The problem with polyurethanes is most of them have tallow in them, which is a big problem in certain markets. Requires more testing. It's a little bit of a sticking point, but in general, they're used widely and get through those headaches. The material is certainly more expensive than PVACs, so that's another drawback. But there are various grades of polyurethane, and a lot of them are better performing than PVACs are. They'll have a better flexural rigidity to strength ratio. There's some that have some polycarbonates mixed in with them, so they have very good flexibility to strength ratios. And again, once you get below 80A, there's no more PVACs that's used in there, and so you're gonna have to go to a polyurethane if you want to get softer there. Then you've got polyamides, which are the stiffest of the range. PVACs actually has polyamide in it, and that's why it's polyether block amide. And so it's a combination of soft material and stiff material in various ratios to get to the stiffness that you're looking for. Once you move to polyamide, you're just talking about stiff. There's various types of polyamides. There's Asno, which is an Arkema product. There's Vestamid, which is stiffer. Those are typically used for your proximal sections or for tubing that doesn't need to be very flexible and needs to be a bit more lubricious. The stiffer the material is, the more lubricious it is, the softer it is, generally the more tacky it's going to be, and your lubricity gets really poor. Polyethylenes, again, like we talked about earlier, high density polyethylene, low density polyethylene, polypropylene, not typically used for an outer jacket because they don't play nice with other materials. You usually have to use a binding agent, use a co-extrusion. So usually they're going to be used for an introducer or dilator where you're just using that material and that's it. PVC, not commonly used in catheters, but it does get used periodically. I'm not going to talk too much about that. Polyimide, really only used, again, what I said before about doing a sandwich layer of polyimide, then your polyimide liner, then your braid or coil reinforcement, and then polyimide again. Not usually used for a jacket other than in that application, size limited. PET, really, so PET, there's PET heat shrink and then there's polyester resins. They are typically pretty soft, but don't play nice with most other materials. And so they can be a bit finicky to try and laminate and get good adhesion between all your layers to the liner, to your braid. Again, they can be really flexible, but aren't necessarily ideal. And then some fluoropolymers, but generally for fluoropolymers, we're really just talking about using them as heat shrink in a structure where you're not braid or coil reinforced, or the braid and coil is already bound by something else, and all you need to do is put like kind of a lubricious layer on the outside. Thermoplastics are all extruded or film cast, most commonly extruded because of the size limitations. They can be run in single lumen and multi-lumens and co-extrusions over the wire. They can be thin, they can be thick. Not as thin as what you can get with film cast. That's where you can get ultra thin, but reasonably thin. Generally lower limits of 1.5 or 2 thou for most extrusions. Occasionally you can get down to 1 thou, but generally speaking, we're talking about 2-3 thou extrusions. And really, this, as far as multi-lumens, the sky's the limit. You see on the right here, we have this picture of the different kinds of multi-lumens. They can get really wild and complex. It's pretty cool. Now let's talk about some of the additives. So radiopacity and lubricious additives are kind of the most common. There's some other types of fillers and additives. I won't really go into detail here about heat and light stabilizers and stuff like that can be added to PVACs and things to make them a little bit more stable. But really, when we're talking about fillers, most of the time we're talking about RO fillers and lubricious additives. So with radiopaque fillers, you see a little chart on the right there with some of these radiopaque fillers and kind of how they show up under fluoroscopy. And that's usually your driving force on which one you choose to use. Barium sulfate is by far the most commonly used. It's cheap, it's widely available, it has good colorability, it's got good thermal stability, and there's just a lot of data on it. And so it's used very commonly, but it does not have the best visibility compared to some of the other options. The next one is bismuth oxychloride. Bismuth oxychloride is used quite a bit as well. It's also it's good, easy to color, low yellowing, good thermal stability, so you can process it at a really broad range of processing temperatures and speeds. The nice thing about bismuth oxychloride is that it has higher visibility than barium sulfate. So you can put it into lower percent loading. And obviously, the more of any of these materials that you add in, you start adding impact to the performance of the polymer. So in general, they're getting stiffer the more of this material you add in there, and you're starting to hurt some of the performance. So with bismuth oxychloride, because it has higher density and higher visibility under fluoro, you can put less of it in there. So typically for barium sulfate, you're talking about 20 to 40%. 20 is really, really common. 40 used in certain devices where you really want some good visibility out of it. And with bismuth oxychloride, we can drop that down to 10, 15%, and usually don't go any higher than 30. So we get impact. But it is more expensive than barium sulfate, so if that's a consideration, then you may stick to barium sulfate. The next two are not very commonly used, and big reason for that, bismuth subcarbonate and bismuth trioxide are not very thermally stable. They yellow really easily. They're not very colorable. They're difficult to run in thinner walls. They are cheaper than bismuth oxychloride, but not as cheap as barium sulfate. So they're available, very specific applications where you're going to use them. Neither of them can really withstand typical reflow processes. So not great for outer jacket materials on a composite structure. Maybe you use them on just an extruded tube where you can extrude them a little bit colder and use them as a dilator or an introducer shaft. And then the last one is tungsten. Last but not least, tungsten's used really commonly. It's a very heavy metal. It is a dark gray in color, almost black. It's typically used in very high percent loading, and it's usually used for tips where you really want to be able to see the tip of the catheter and know exactly where it is in the anatomy for executing your procedure. It's usually run 60, 70, up to 80% loading. So there's a lot, you've got more metal than you do your actual polymer. You're not going to color match it unless you're talking about using black, especially at 70 or 80%, because it's very dark gray in color. You're just not going to get a color match. But that's fine. Again, it's typically used for a tip or some sort of a marker band that you embed into the shaft. But it's certainly going to give you more visibility than any of the other fillers in this table. Problem with tungsten is you're using it at a really high percentage. It's particulate, it's little particles. The strength of the material falls off, and there's been some issues in the industry where the tips aren't bonded very well to the next material adjacent to it, and they've fallen off because they tend to be a little bit more brittle. So usually it's a good idea to overlap materials with tungsten tips or markers and not just butt weld them. So then we go into lubricants additives. I like Propel. I'm partial to Propel. It's a Foster product. The biggest reason for that is it's PTFE based. It's very inert. It doesn't have, it has a high compatibility with almost all materials. It doesn't leach. It doesn't leave residue. It doesn't cause bonding issues with other materials or with adhesives. And it's got very high lubricity compared to some of the other options out there. So it's one of my favorites. They make 3 different flavors of that. Propel regular is a white material, so you can color it, but you're not going to have it clear. Propel T is a transparent material, so it's optically clear. You can see through it. You can color it if you want to whatever color you're going to use. But for the applications where you actually want to be able to see through your resin, Propel T is your option. And then more recently, they came out with Propel Plus, which is essentially the regular Propel. It's white. It just has a little bit more lubricity than the original Propel did. There's Mobilize compounding solutions. I'm not sure exactly what the structure of Mobilize is. That information is not public, but it has good lubricity. It's not as good as Propel. It doesn't seem to have a lot of leaching issues, but there is more than there is with Propel, and it seems to be good for thermal processing and adhesive bonding. So the last one is siloxane, which is silicone. The problem with siloxane, and a lot of people try not to use it. It is the best for lubricity because it basically leaves a silicone oil residue on the outside of your part, which is bad for a lot of things. It's great for lubricity, but terrible if you're trying to bond it to other things. It contaminates your room, it contaminates extruders, it makes bonding it with adhesive virtually impossible. And so most people, unless you absolutely need it to be that lubricious, don't use siloxane. And a lot of companies don't want to extrude it because it contaminates their systems, and it's just not ideal. And that's really kind of the end of it. So I'd like to move into the Q&A now, and if anyone's got any questions, I'd love to answer them for you.
Okay, so we're going to move into answering any questions that our attendees have. So just as a reminder, just look for the questions icon, click on that. It will open up the questions panel and you can type any questions that you have. And Jordan, are you there?
Yeah, can you hear me?
Yeah.
Perfect.
Okay. Let's see. I think I've got a couple that have come in.
Okay.
So the first one here is, what is the issue with tallow and PU biocompatibility?
So, I'm not a regulatory person, but there's been issues with regulatory path for tallow. Tallow is a beef animal product, and so there's concerns about mad cow disease and other biologicals. And so it's been kind of a big issue for a while. And a lot of the Lubrizol materials contain tallow. It's just an element that's used to make thermoplastic polyurethanes. There's been some reformulations coming out to try to remove tallow, but it is a pretty important component. So I don't know how well they've been doing at getting that out of there and maintaining good performance out of those materials. But again, it's a concern by the regulatory bodies, but it hasn't been an issue for the most part. It just takes a little bit more testing and a little bit more rigorous filings to get it through than materials that don't have it in there. And it's primarily an issue with the EU and less of an issue in the US market and a lot of other markets. So it's certain industries and certain markets are more challenging than others.
Great, thank you. Next question, how does the process of braiding flat wire differ from braiding round wire?
So it really doesn't vary at all. The materials are kind of self-orienting when they go through the braiding process. The braiding carriers and the rollers the wires pass through orient the wires, and then as they lay down, especially if the rounds don't care if they're misoriented because they're round, they're symmetric. The flat wires, you would think, oh well, they could roll over on themselves and twist and cause those problems. That's a bigger problem with really big flat wires that have a lot more rigidity to them. But the smaller wires are very self-orienting. When they go and lay down onto the shaft, they want to go in the path of least resistance, and that's the big flat side. And they don't tend to roll over. Sometimes you can run into that a little bit with really big wires that want to fight that, but it's not very typical to have those problems.
Great, thanks. And I do have a comment from Walter saying great presentation. So I think he's going to be sharing that with students as well. So
awesome.
And another question, should choice of liner material influence braid coil material? How deep usually these metals embed press into the liner layer?
Can you read that again?
Yeah. Should choice of liner material influence braid coil material? And how deep usually maybe are these metals embedded or pressed into the liner layer?
So the thing to consider when you're talking about different liners with different reinforcement layers, coils have a hard time with, especially round wire coils, don't like to be put over a substrate that's going to be that's going to melt, right? So if you're doing a coil over the top of a thermoplastic liner, um, when that underlayer melts, it loosens the coil. It relaxes because now there's not a solid substrate underneath it anymore, and it causes the pitch to move around and become inconsistent. And it can be really bad, especially with a round wire that really just wants to move around. On ribbon wires, it's not as bad. More surface area, they're a little bit more stable. It's a little harder for them to move, even if the underlayer is melting. The thinner that underlayer is, the better. If you're going to have it be melt processable. For PTFE, it doesn't matter. For any of those other non-melting at your processing temperatures materials, they don't care. So a lot of times when I'm going to run a coil over a thermoplastic, I'll put the coil on top of the braid because the braid gives you that more solid structure. There are performance differences between braid being under or over coil in certain applications, but it's, I think you're going to have a bigger problem with your coil walking all over the place than the benefit of having the coil underneath versus over the top of your braid. As far as indentation, again, it depends on the material. If your liner is really soft, your indentation is going to be more significant because your force is going to indent that material more. With really thin liners, PTFE liners, stuff like that, you don't see a significant amount of indentation. But if you're running a non-metallic core, like a PTFE monofilament as your core, which is somewhat soft, then you could indent that as well, not just the liner, and cause some ID constrictions on your device. But you can manipulate that with how much tension you have on your braid or coil. Usually, it's going to be worse with a coil because of single point contact versus a braid, where you're getting that braided structure doesn't dig in as badly as a coil might. But you manage that by reducing the amount of tension in the wires to mitigate that and reduce the amount of dig you get in with that.
Thanks, Jordan. Next question. Do you have comments on laser cut hypotubes, advantages, disadvantages in relation to braided products?
Yeah, we left laser cut hypotubes out of this intentionally because they're their own beast. We will likely do another webinar on that later and really go into detail about the laser cut hypotubes. We use them quite a bit and we're using them more and more. They do have performance benefits over braid and coil reinforcement. They are more expensive, so the applications that you're going to use them in are going to be ones that really require that additional level of support that you're going to get from that. Also, you can get a lot thinner device out of a laser cut hypotube reinforced device over braid and coil reinforced devices, and generally better tolerancing out of it. So I'm not going to go into too much detail on that one here. We will most likely have another webinar and we can go into more detail then.
Okay, thanks. And then what are the factors that people should consider during the secondary processing? Can you comment on when people use reflow or thermal lamination in the secondary process?
Well, reflow and thermal lamination are the same. That they're a thermal process. Generally speaking, when we're talking about building a catheter, we're talking about a base layer of liner, some more reinforcement, a jacket layer, and then we put heat shrink over the top of that and use that as our compressive element to force the layers together when we heat them. So we're melting the plastics and the heat shrink is forcing that melted plastic down through the layers. The other type of process is dip type casting, where the material for the jacket is broken into solution. Generally speaking, all these polymers are solvatable. They can break down in solvents. For TPUs, you're talking about THF, and for PVACs, M-cresol. So you can do a dip process or some other types of deposition processing there, but reflow and thermal processing are one and the same.
Great. Another comment, thanks, very informative session. And then I think this looks like it might be the last question for now. So if you still want to get your questions in there, now's the time. What are the factors that people should consider during the secondary? Oh, no, I just read you that one, didn't I? Yeah, I'm rereading questions now. Sorry about that.
Yeah, one other point there with thermal processing, there are a lot of considerations with how you do thermal processing. So same thing, that's kind of its own webinar to talk about actual processing techniques, besides just catheter construction techniques. But with thermal processing, you're using one of two different types of machines. Typically, you're using either a forced air convection system like the beam or the MSI lamination systems, or you're using a radiant body type heating system like the R&D engineering machine. And there's a few others out there, but the radiant systems are better for bigger devices that have a lot of thermal mass. And you're going to have a hard time penetrating through that with hot air convection that's blowing at the outside surface and needing to penetrate from the outside in. Radiant bodies work a little bit better for those, because if you hit them with a lot of forced air, you'll overheat the surface before the inside gets hot enough to fully process the device, and you'll start to cause bubbling and material degradation on the outside surface. So it is important to think about what types of processing methods you're using depending on the device that you're doing as well.
Right. Thanks for saving me there. Um,
No problem.
since I now have the questions organized properly here. So there is another one. Is there anything we need to take into account if we plan to bond to a balloon?
Yeah, bonding to a balloon is, um, there's different types of balloons, different type of materials. Some of them are easier to bond to than others. A lot of balloons are silicone. You're not going to thermally bond to those. You're going to have to do adhesive bonding to that. So that's one consideration. Having highly dissimilar materials that you're bonding the balloon to the shaft can be a challenge. You don't want to have materials that are very different, because they don't tend to bond to each other as well. Really soft or really stiff doesn't tend to bond very well. Materials of different families can be a bit hit and miss. Urethanes to PVAXs, especially if you're talking about a high durometer PVAX to a low durometer urethane, they don't tend to like to bond to each other very well. So those are things to think about when you're bonding balloons to a shaft. Urethane balloons and other types of balloon materials that are thermally processable. Obviously, when you're processing those, you've got to be careful about not damaging the balloon necks and heat affected zone coming from the type of heating you're doing. So heat shielding is important to try to mitigate balloon damage. You can always glue them, but gluing is not the preferred method. It's harder to validate. It's less consistent. Thermally bonding is preferred, but sometimes it's really tough to do that because you're going to damage the balloon by doing it. Similar with other construction techniques, there's a lot of different methods for doing these types of things. Balloon bonding, ideally, if you can afford it, buy a laser bonder, because you're going to get the best, the minimized heat affected zone from a laser versus trying to do any other thermal process with heat or a radiant. The laser will put heat in a very, very specific area with a very specific heat affected zone that you can manage.
And there is a question just around who to contact or any contact info in case they still have questions.
That's a good question. Medix is a contract manufacturer and design development house. We are here for companies and startups and physicians and venture capital back or whatever. We're here to help companies out, get their products developed and to market.
All right. And can you have wires in the walls of the catheter?
Any other questions?
Yeah. Did I lose you? Can you hear me now? Okay. It looks like he may have lost audio.
I can't hear you, Karina.
Can you hear me now?
Yeah, that's weird. Can everyone else hear me still? Okay. A question. Yeah, can you have wires in the walls of the catheter? They are in the wall of catheter typically, right? So when you layer these up and you put your jacket over the top and you put heat shrink on that and you thermally fuse, you're melting the plastic and it forces it down through those polymer. Forces the polymer through those wire layers, and now you have wire embedded within the wall of that polymer. So that is your typical composite melt process catheter or dip cast. Either way, you're getting that outer jacket to fill in the voids around the structures and create a solid composite.
All right. Can everyone else hear me okay? I know I saw a thumbs up earlier. Yes. Thank you all so much. All right. I think I'm just making sure. Okay, it looks like there's just one more question, so hang with me because I'm going to assign it to Jordan so he can see it.
Signal wires. Can you elaborate? Do you mean like electrical conductive wires?
Yes, so I see that. Let me just send that to Jordan.
Yeah, you can put signal wires in the wall just like you can braid. And you can put them in various ways. You can put them in axially, again, but those are not fantastic because they tend to break them because all of the bending bias and forces put into them. But you can put them in the braid. You can replace some of your braid element wires with conductor wires. You can use braid wires as conductor wires. You can coat them. Um, so there's a lot of things you can do there.
All right.
And I
So
can
I
use
don't see any.
weird.
Oh, you can hear me now. Okay. All right.
Yeah.
All right. Well, thanks for playing along with that. And we ended up getting those questions answered regardless. So that's good. But I think we're going to go ahead and wrap up. Jordan, is there any final comments you wanted to add?
Um,
Because I know there was a question
no.
just about contact, like I think how to contact, or is there contact a phone number or email or for additional questions or anything like that?
That's a good question.
Or we can include it maybe in the follow-up email.
Yeah.
All right. We'll do that. All right. Well, thank you so much, Jordan, for your presentation. And an email to all attendees will be sent out in about a day with a link to the recording, as well as a link to a brief survey. And we would really appreciate if you could take a moment to complete the survey because we do value your feedback. And on behalf of Medix, we'd like to thank you for taking the time to join our session, and we hope you enjoy the rest of your day.
Thanks, everyone.